As usual, it's a very great pleasure for me to be here at the KITP. And as David already mentioned, stars after their death go through a second life. And I want to tell you about this second life because many interesting things happen even in the second life of a star. And these neutron stars, which is one of the most spectacular types of forms of life after death, they are really extreme objects. Picture a star which is not larger than Santa Barbara and Goleta together, the diameter of about 12 miles, 20 kilometers, we say in Europe. Just a ball of matter, which contains about 400,000 times the mass of the Earth, compressed in this little ball of 12 miles diameter. That's a neutron star. The density in a neutron star is such that in the volume, well, we had a lot of rain today, in the volume of a raindrop, you have as much matter as of the entire world population together. If you put all the 6.5 billion people, the matter of 6.5 billion people in the volume of a pretty large raindrop, then you have the density of a neutron star. Now, to understand how such extreme objects could form, and we know thousands of them already in our galaxy and also in other galaxies, how they might form, I have to give you a little crash course in astronomy to get the framework and the idea where everything fits in. And so I would like to start. Oh, the thing went off. It should not do that. I would like to start. We know now that the universe exists for 13.7 billion years. It started with the Big Bang that time ago. We also know that galaxies and our galaxy were around already for at least the last 13 billion years. They formed in the first few hundred million years after the Big Bang. We also know that the solar system and the Earth exist for 4.65 billion years. So the universe was already 9 billion years old before the Sun and the Earth and the planets formed. We know this from radioactive studies of meteorites which fall on the Earth, and the oldest lunar rocks which the asteroids brought along. The oldest stones in the solar system have that age, and we think that is the age of the solar system. We also know that the universe started out only, the Big Bang could only make hydrogen and helium and a little bit of some other light elements like lithium and beryllium, but basically hydrogen and helium, and not the normal elements that we know about. And as David already mentioned, these elements were produced in the stars. We now know that they are produced in massive stars. These live very short. At the end of life, they explode, and then they leave behind these funny things like neutron stars or black holes. And we owe our existence to these the evolution of massive stars which live very short and then dump all the elements which they have made in their interior. They bring it back in the hydrogen clouds in our galaxy, and from that form new stars. And when the solar system formed, that had been going on already for 9 billion years. And so this tiny little bit, a few percent of the matter in the universe is in the heavier elements, something like 86 different heavier elements, and these are vital for us here on Earth, of course. Now, what is a star? The Sun is a star. That's our star. And you see the Sun is a gigantic thing if you compare it to the planets. The Earth is 100 times smaller in diameter than the Sun. And the mass of the Sun is 330,000 times the mass of the Earth. The Sun consists, like most matter in the universe, out of 70% hydrogen, very light gas, 28% helium, and a few percent only of all these heavier elements that we know, like carbon, oxygen, iron, etc. The big planets like Jupiter and Saturn have the same composition as the Sun. It's mostly hydrogen and helium. They are what we call gas giants. But the little planets like the Earth and Venus, they had not enough gravity to keep these light elements like hydrogen and helium. We lost it, and we only have the rocky residual of the original matter. The Earth, there is hydrogen still in the oceans, of course, but bound to oxygen, hydrogen is still there. You see that all the planets together is very little mass. It's only about 1/1000th of the mass of the Sun. So 99.9% of the solar system is in the Sun, and only 1/1000th is in the planets. The planets is just a little bit of dust, specks of dust left over when the Sun formed. And I don't want to give you an inferiority complex, but the Earth is really very small. If you see it here, the Earth is tiny in comparison. If you see this, it is evident that, of course, what Copernicus discovered, that the Sun is in the center of the solar system, because the planets is really very, very little. Okay, that's about the Sun, our star. But now we also want to know how far away are we from the Sun. And of course you know that we are the third rock from the Sun, the Earth. We have Mercury, Venus, then the Earth plus the Moon. We have Mars, we have Jupiter, and we can make them also start moving. And you see that the inner planets move faster than the outer ones. Yeah, and how far away are we from the Sun? We are 150 million kilometers away from the Sun. Our position here, it will stop, is 150 million kilometers. In astronomy, we always express these distances in the time that light need to travel this distance. And light goes 300,000 kilometers in a second, so it's about 500 seconds from the Sun to the Earth. It's about 8 minutes. So we see the Sun as it was 8 minutes ago. If the Sun would disappear now, you would notice it 8 minutes from now. The most distant planet in the solar system is Neptune. Very unfortunately, Pluto has been demoted to a dwarf planet. So Neptune is about 4 light hours away. We see Neptune as it was 4 hours ago. And for example, if there is a satellite near Neptune and you want the satellite to take a picture, the radio waves travel with the velocity of light. So if you send a signal, take a picture, the signal arrives there 4 hours later, and then 8 hours later we know whether this picture has been taken. And that's the biggest distance in the solar system of a planet. Now stars, these other balls, glowing balls of gas, are much farther away than the planets. The nearest star is more than 4 light years away, 4.2 light years away. And so the light takes 4.2 years from this nearest star to us. If we want to compare that to the distance of the Earth and the Sun, for that reason I took this orange along, and this is the Sun, and I also took the Earth along, which is the head of a pin, which I have here. You cannot see it, I'm afraid. And now I need Americans are very sportive people have told me. And I need someone who is sitting 33 feet away in the back. And if there's someone who is good enough to catch, yes? Very good, thank you very much. You are 33 feet away. And on the scale of, this is exactly the scale as it is in the solar system. The orange is 100 times larger than my pinhead, and there fit about 100 of these oranges between us. On that scale, Neptune is still on the campus of the university here. But the nearest star is 2,600 kilometers away. The nearest other orange is in Chicago about. So the distances of the stars are enormous. And even the farthest space probe has the Voyagers and the Pioneers have traveled not further on this scale than Hollister Avenue here in Goleta. So travel to the stars is not an easy matter. The distances are enormous. And this 4 or 5 light years is typical for the distances between the stars in our galaxy. We know since about 80 years how our galaxy looks like. Oh, sorry, the distances of other stars. I would like to tell you a few stars that you can see at night. Yesterday night I just looked at here at Orion. You can see it very well. And we have in the constellation of Orion, for example, this star is 800 light years away. If you are at that star, you see there just arrived the light which left the Earth 800 years ago. So you can still see the Crusaders mounting their horses to go to Jerusalem. This star is 2,000 light years away, the middle one of the belt of Orion. Alnilam is the name of that star. If you look from there at the Earth, you can still see the Romans entering Britain. What you see here is that the further you look in the universe, the further you look in the past. And that's all because the velocity of light is finite. This is one of the few equations which I'm going to show today. Far away is long ago, because the velocity of light is finite. If we look at the galaxy a billion light years away, we see it as it was a billion years ago. If we look at the galaxy at 10 billion light years away, we see it as it was 10 billion years ago. We see the whole history of the universe standing on the sky. Basically, it's all fossils what we see, because they have already themselves evolved since the time that the light was emitted. But the astronomers can study the whole evolution of the universe by looking at objects farther and farther away. Now we know that our galaxy, we know since about 80 years that our galaxy looks more or less like this. This is of course not our galaxy, but it's another spiral galaxy. It's a flat system. If you look from the side, it looks like this. And it has a diameter of about 100,000 light years. And the sun is about 30,000 light years away from the center and moves around the center in about 220 million years. The galaxy has about 100 billion, probably even more. It probably could be easily 200 billion stars, more or less like our sun. We know that since about 1923. That we are not in the center, but that we are just one of the stars far in the outskirts. Until 1923, people thought that our galaxy was the whole universe. But then Edwin Hubble came here at Mount Wilson, and he had the largest telescope then at Mount Wilson, the 100-inch telescope, and he started looking at nebulae. And people knew nebulae. They thought maybe they are gas. Some people thought certain nebulae might be other galaxies, but nobody knew for sure. But when he had this big telescope and he looked at the Andromeda Nebula, he discovered in the outskirts of the Andromeda Nebula stars which looked like the brightest stars in our own galaxy, which emit something like 100,000 times the light of our sun. And he saw them as very faint specks of light in the Andromeda Galaxy, which means that the Andromeda Galaxy must be very far away, and we now know it's about 2 million light years away, and that it is a galaxy like our own. On this picture, you do not see the separate stars in the Andromeda Nebula. All the other stars which you see here are stars, foreground stars from our own galaxy, and the Andromeda Nebula is behind that. So these are just stars like the sun. And it could be that someone here is also listening to a talk about neutron stars. You never know. It's probably not very likely, I'm sorry to say so. Okay. If you look from there at the Earth, you see in Africa just the first ancestors of us starting to make Stone Age tools 2 million years ago. The most distant galaxies we see are about 13. The light has been traveling for about 13 billion years. This is a nice galaxy which is 65 million light years away on the southern sky. If you look from there at the Earth, you can still see the dinosaurs just dying because the Earth was hit by an asteroid 65 million years ago. Okay, this was a very brief introduction to the universe. Now about stars. What is so special about stars is that they emit so much energy. If we look at the sun emits every second 4 times 10 to the 26 joules in energy. And so it is a light bulb of 4 times 10 to the 26 watts, 26 zeros here. 1 second of what the sun emits is about enough for the energy consumption of the world population for about 1 million years. And that just disappears into space all the time. Only a very tiny fraction falls on the Earth, and that is still something like 10,000 times what the human population consumes. So there is not a real energy problem if you really come to look at this. Now we know that the sun must have been doing that for almost 4 billion years at least, because we know that people have found fossil single cells organism in the rocks in Greenland and in Canada, which are at least 3.8 billion years old. And so life on Earth has been there already for almost 4 billion years. And life requires that it's not too cold and not too hot, but it must be about what it is now. And so the sun has been shining for at least these 4 billion years. And how does it do that? Well, it was found by physicists in the late 1930s that the sun does this by using its own hydrogen as a fuel. The hydrogen, which is 70% of the sun, is the fuel in the sun. And it does it by nuclear fusion. I have to get accustomed to this little thing in my hand. What happens is the nucleus of a hydrogen atom we call a proton. It's a positively charged particle. And there is also a particle called a neutron, which has about the same mass but has no electric charge. And all nuclei of atoms consist of these protons and neutrons. Basically, the neutrons is a kind of glue because the positive charges repel each other, and to keep them together you need these neutrons to glue them together. Now the nucleus of a helium atom is basically 2 protons and 2 neutrons. And you would think that if you would put 2 protons and 2 neutrons together, that you would just have the mass of 2 protons and 2 neutrons, but a helium nucleus is lighter than that. If you would be able to put 4 protons together and make a helium nucleus out of it, you would lose 1/34 of the mass. Now Einstein had this famous formula that energy and mass is equivalent. Energy is mass times the velocity of light squared. The velocity of light is a very large number, 300,000 kilometers a second. So a tiny bit of mass gives an enormous amount of energy. And so if you would be able to put these protons together and get rid of 2 of these positive charges, you would and make helium out of hydrogen, then you would get an enormous amount of energy from a little bit of mass. And for example, from 1 gram of hydrogen, something like a thimbleful of water, you get, if you would fuse the hydrogen in there to helium, you would get enough energy to drive a Toyota Corolla once around the Earth. And this is what the sun does. You can only do it if you have a high temperature. If you would like to do it on Earth, you would need something like 100 million degree Kelvin. But in the center of a star, it can happen already at a lower temperature. In the center of the sun, it's about 14 million Kelvin, and there this fusion takes place. And the sun fuses every second, it burns every second, 600 million tons of its hydrogen. And of that, this 134th part, this is about 4 million tons, is completely converted into energy. And that is what is being emitted every second. You could say 600 million hydrogen bombs a second, but It's not hydrogen bombs because the sun does it in a very gentle way. Now the sun has an enormous amount of hydrogen, more than 300,000 times the mass of the Earth. And how long will it burn on that? Easy calculation, you know how much it does every second, you know how much hydrogen it has, you divide the two, and then you find that the sun takes about 10 billion years before it is through its hydrogen. Now we are only 4.65 billion years old, so we still have lots of time. I mean, you can have sleepless nights about the warming up of the Earth or for other things, but the only thing you never have to have a sleepless night about is that the sun will disappear, because for the next 5 billion years it will still be nicely shining. But this is not the case for very massive stars, because if I take a star which is 25 times more massive than the sun, and we know such stars, the stars in the belt of Orion, which I showed you in this Alnilam star, which is 2,000 light years away, that's a star of about 25 solar masses. Such a star emits about 50,000 times more light than our sun. And that means that it burns every second 50,000 times more hydrogen than the sun. But it has only 25 times more. It burns 50,000 times more, but it has only 25 times more. If you have 25 times more money than your neighbor, but you spend it 50,000 times faster, you are much faster through your money. And this guy is much faster through its hydrogen. You can just divide those two things. It lives 2,000 times shorter than the sun. It's only 5 million years. So these stars in Orion, these bright stars, they are spending what they have, their money, so fast that they are through in a very short time. And so the question is, what happens after them? We see those massive stars at many places. I mentioned Orion, but for example, there is a nice nebula in the Milky Way, in the constellation of Monoceros, the Rosette Nebula. You see these big blue stars here. Those are stars of 20, 30 solar masses. They cannot be older than 5 million years because they will be gone. They have finished their hydrogen in 5 million years. They live a little bit longer on the helium and carbon and other stuff, but that's much shorter. The hydrogen burning phase lasts the longest. And so these guys must be younger than say 5 million years. They just condensed out of this nebulous material, what you see here, and with the enormous ultraviolet light which they are emitting, the amount they are emitting, they are ionizing the nebula, and they have blown this hole in the nebula. So they are basically destroying the cloud from which they just recently condensed. Also, many small stars condensed from that cloud, and they will live like the sun almost forever. But we see these things. And so the question is, what happens when a star dies? Now that was discovered by accident already in 1862, although people had no clue that this was a dead star. This is the companion of Sirius, the brightest star of the sky. Sirius is the brightest star of the sky, and in 1862 a lens grinder here in the United States, Alvan Clark, discovered when he was testing a lens that Sirius has a tiny little companion star. And this companion runs around, the two stars orbit around each other in 50 years. Now this is fantastic because then you can use the gravity law to measure what the masses of the stars are. And it turns out that the main star, Sirius, the brightest star of the sky, has a mass twice that of the sun, but its companion, which we now call Sirius B, is as massive as the sun. But astronomers can also determine how large, what is the diameter of that star, and it turns out it is not larger than the Earth. So this is a very strange star, 330,000 times the mass of the Earth. It is as massive as the sun, but it is not bigger than the Earth. The same volume, but you have 300,000 times more mass in this volume. Now the Earth, the rocks and the metals is about 5.5 kilo per liter. And so this is 300,000 times as much per liter, and it's about 1,700 tons in the volume of a pack of milk from the supermarket. That's about 5 jumbo jets with passengers squeezed in a pack of milk, which is a lot. And so people, when they discovered that was around 1910, people were flabbergasted. How can a star have such a crazy density? 1,700 tons in the volume of in a quart in the volume of a pack of milk. These stars are not rare. We know more than 10,000 of them, and I'm proud to say that one of my former countrymen, although he became an American quite young, discovered 6,700 of them. He was like a stamp collector. He loved white dwarfs and discovered 6,700. Willem Luiten discovered. He had a long life, by the way. Yeah, how? Because you see, he lived to the age of 95 in Minnesota. Yeah, how can a star have such a density? People started to understand that only in around 1925, when people began to understand how atoms are built. Now, the amazing thing is always, if you want to know how such a big object behaves, like the sun, you have to know what the atoms or the nuclei of the atoms are doing. And the same is the case now with these white dwarfs. If you want to understand why these have such crazy densities, then you have to know how atoms are built. And it turns out that an atom is largely empty space. I have here a hydrogen atom, and an atom consists of this positively charged nucleus and then a negatively electrically charged electron going around it. And all other atoms have similar structures, but more protons in the nucleus and more electrons in orbits around them. They are held together by these electric forces, you could say. Now, the diameter of this nucleus is tiny. And the size of the atom is determined by the size of the electron orbit. And in a hydrogen atom, the lowest orbit an electron can have is still 50,000 times larger than the diameter of the nucleus. So the atom is largely empty space. If you would take a proton the size of a pinhead and you put it in the center of a football stadium, then on the right scale, the electron is running at the edge of the football stadium. It's largely empty. And so, basically, you could compress normal matter still by an enormous factor, because 50,000 times, space is three-dimensional, so the volume is 10 to the 14, 50,000 to the power 3. It's about 100 trillion times larger than the volume of the nucleus. So there is still a lot of room for compression of normal matter. The only trouble is electrons do not like to be compressed like that, because all the matter you have here and of which you consist, basically we never see a nucleus, by the way, you only see electrons. All what you see around you here are the electrons of the molecules, and so in the paint and in your neighbor and in whatever, you only see electrons, you never see nuclei. But they don't like to be compressed, and if you want to compress normal matter so much that the electrons are pressed into the nuclei, you need a pressure of about 10 to the 30 times the atmospheric pressure here on Earth. Now, nobody on Earth can make pressures larger than about 1,000,000 bar, so you're short by a factor 10 to the 24. If you press an electron into a nucleus, into a proton, you get a neutron and also a little particle, which I completely ignore for the moment, comes out a so-called antineutrino. But you get this neutral object. So if you would really compress all the matter, you would just get a ball of neutrons. Now, in a white dwarf, this has not happened yet. The only thing, the pressure due to gravity, because all the parts of the white dwarf attract each other by gravity, they produce an enormous pressure in the center of a white dwarf, about 10 to the 18 bar. Then they already crush the atoms. So in normal matter, still the inner electron orbits are still undisturbed, but if you start compressing very much, that the nuclei are closer together than the smallest allowed electron orbits, then the electrons don't know where to go, and they start to roam around between the nuclei, and they behave as a quantum gas. And that was discovered in the 1920s, how they behave. And then people understood that this is the situation in a white dwarf. The matter has been compressed so much that these electrons are a quantum gas which is able to press against gravity. But still there is a lot of empty space in a white dwarf. Even though it has 1700 tons per liter, it's still mostly empty space, but very much compressed. And we call that degenerate matter. Now, 1925, it looked like this was solved, but then there was a young boy from India, a 19-year-old boy, and he got a fellowship to go study in Cambridge in England. And in those days you went on a boat, because it did not fly yet from India to England, and it takes about 3-4 weeks. And he had nothing to do, so on the boat he started to calculate how white dwarfs of different masses behave. 19-year-old guy. There we have him. He was born just 100 years ago this year, Chandrasekhar. And when he was calculating how the radii, the sizes of white dwarfs of different masses behave, he found that if it's half the mass of the Sun, it's about 20,000 kilometers. If it has the mass of the Sun, it's about as big as the Earth. And if it's the more massive the white dwarf becomes, the matter attracts each other by gravity stronger and compresses everything stronger and stronger. And then he discovered, to his great surprise, that if you make the mass larger than 1.44 times the Sun, the electrons can no longer press hard enough against gravity and the thing would collapse. And he thought, this was in 1930, he thought that you would get something like a black hole then, because there was no force known which could withstand gravity then in a white dwarf. The neutron was discovered only in 1932, 2 years later, and he didn't know neutrons exist. And immediately when in 1932 the neutron was discovered, there was a Russian physicist, Landau, who calculated that you can make stars out of neutrons also. And then all the empty space has been squeezed out, and you only have left a ball of neutrons. And there the same holds. Well, this is a very primitive way of representing it, but also if you make them more massive, they get, well, depends on how stiff the matter is, but they tend to get a little smaller. But if they get more massive than about, these neutron stars get more massive than about 3.5 times our Sun, there is nothing that can withhold them from collapsing to a black hole. I'm sorry this is Dutch language. This is the Sun, is the zon in Dutch. So this was Chandrasekhar, 19 years old, calculated this. He got the Nobel Prize 53 years later for this. And so when the Nobel Committee called, his wife picked up the phone and she said, well, it was about time. And no, really, literally, she said that. He told me this one. Yeah. And it was time, indeed. So this neutron star is about a little over 400,000 times the mass of the Earth. It's not bigger than Manhattan. Yeah, and we know from Einstein, a neutron star has enormous gravity because you have all this matter packed so closely together. The gravitational acceleration on the surface is 100 billion times that on Earth. If you weigh here 120 pounds, you weigh there on a neutron star, you weigh 100 billion times 120 pounds, and you would have great difficulty to put one foot in front of the other. You would be squeezed really to nothing. And to get out of a neutron star, you need about half the velocity of light. If you want with a rocket to get out, that's the escape velocity, is about half the velocity of light. Light can still come out. And Einstein said, of course, that when you have strong gravity, space-time is curved, and space itself is curved, and you can represent a neutron star like a kind of a pit in space, but a pit with a bottom. And on the other hand, a black hole is a bottomless pit, so it's infinitely deep. And this was all calculated already in the late 30s by Oppenheimer here in Berkeley with his students. He was the first one to make decent calculations of neutron stars and also of black holes, the same Oppenheimer who later led the Manhattan Project. These were theoretical objects. But so when you want to get out, you need half the velocity of light. But if now the burned out core of a star is more massive, larger than the Chandrasekhar mass, this core will collapse. And when it forms a neutron star, suddenly this neutron star is very hard, all the falling in of the matter stops. With what speed does the matter fall in? It falls in with the same escape velocity. If you want to get out, you need half the velocity of light. If you drop a stone on a neutron star, it will fall in and arrive at the surface with about half the velocity of light. And the same if this whole star collapses, or this burned out core of a star collapses to a neutron star, it falls in with half the velocity of light. And the energy of motion, sorry, I'm pressing all the time the wrong button. The energy of motion of a moving object is half times the mass times the velocity squared, and the velocity is half the velocity of light when the neutron star forms. And so suddenly this is all stopped, this infalling matter. And now this is like when you drive a car against a concrete wall. Suddenly you get rid of all the mechanical energy, and that's used to wrinkle your car into wrinkled metal. But here, this energy must go somewhere, and so it goes into heat, basically. And the amount of heat which is produced in a few seconds when this collapse takes place, this amount is so gigantic, it's about 1,000 times what 1,000 billion years of sunshine, 100 times as much as the sun emits in its whole life. Now you would expect to see something of that if a star collapses to a neutron star. If so much energy comes out in a few seconds, you would expect to see something spectacular. The energy is by far enough to blow the whole rest of the star out. And already in 1934 there were two astronomers, again here from Mount Wilson Observatory, who realized that this could be the cause of what one calls a supernova, an exploding star. These were discovered only in the 1920s that those exist. These stars can get, for a couple of weeks, as bright as an entire galaxy, and their suggestion was, hey, those stars could be produced by the collapse of the burnt out core of a star into a neutron star. So that was their idea. And these supernovae, and this is a supernova, one sees many of them in other galaxies. You see one here which appeared in 1998 in this nice spiral galaxy. It was photographed by a telescope on the Canary Islands. And during about 3 weeks, this star is about 1 billion times brighter than the sun, such a supernova. It emits an enormous amount of energy. They are rare. They happen in a galaxy not faster, not more than, say, once per 30 years or one per 100 years. But that means that astronomers nowadays look at tens of thousands of galaxies. And if you look at 10,000 galaxies, and it happens per galaxy once per 100 years, you still see 100 supernovae per year if you look at 10,000 galaxies. And so you see many, many of them per year. And here I've just a couple of pictures of supernovae. This is one which appeared here in 1994. It was, these letters indicate that this is number 4 of that year. They're given letters from the alphabet. And if you're through with the first 26, then you add another letter. And this is one out of 2003. And this is a galaxy where there appeared 2 of them 1 year after the other. That's quite amazing that this galaxy had, in 1 year time, had 2 supernovae. But one sees many, many, many of these supernovae. And one wonders also, did one see supernovae in our own galaxy? And indeed, from historical records, we know that there were supernovae that happened in our own galaxy. There was the famous star of 1572 of the Danish astronomer Tycho. That was a supernova. He observed it for more than a year and wrote a whole book about it, 1572. Kepler saw one in 1604. And with radio telescopes and X-ray telescopes, you find many shells of these exploding stars, because when the star explodes, the outer layers are kicked out, and with a very large velocity, thousands of kilometers per second. And so they expand and they sweep up interstellar gas and dust. So they are decelerating, but they keep to be visible for about 50,000 years before they dissolve into the interstellar clouds. And so this is one of a few thousand years old, where we have an X-ray and a radio picture superimposed on each other. This is the star of 1572. This was not one which produced a neutron star, by the way, but this was also a famous supernova. And one of the most famous ones was a star which was seen in the year 1054. It was even visible then during daylight, and the Chinese and the Koreans and the Japanese astrologers have made a good record of that case. And we see there now this nebula, the Crab Nebula, in the constellation Taurus, which is there. It's not very rapidly expanding, only 1,500 kilometers per second. And if you calculate back, indeed, it must have happened around the year 1000. We thought until recently that it was not seen in Europe, but an Italian astronomer digging in the archives of the Vatican found a record by a Flemish monk who has seen it also in 1054. So it has been seen also in Europe. It was not so clear why there are so few records of it in Europe, but in any case, this was a very bright supernova. Now, this was the whole story up to 1967. People had the idea, Bade and Zwicky, 1934, supernovae could be produced by the collapse of the burned out core of a star to a neutron star. But that was it. But then, the year 1967, there was a student in Cambridge in England, and her boss had built, Professor Anthony Hewish, had built a very large radio telescope consisting of just wooden poles and many acres of wooden poles and copper wire, many, many miles of copper wire. It's just an antenna, a radio telescope, and he wanted to study the rapid variability of extragalactic radio sources. And he hired Jocelyn Bell, and already in the first year of the telescope, Jocelyn, in November 1967, discovered a radio source, and she knew that it was part of the stars, because you can only see a radio source with this funny telescope if it is for a couple of tens of minutes above this antenna. So you use the rotation of the Earth, and when the radio source is just above you, you can detect it for a couple of tens of minutes, and then it disappears again. So you use the turning of the Earth. And the Earth turns in 24 hours minus 4 minutes, and this source also turned around, came back every 24 hours minus 4 minutes, so we know that it was among the stars. And this source shows these funny pulses every 1.33 seconds. This just looked like a man-made signal. And so in the beginning, they were afraid that they had discovered an extraterrestrial civilization. But then by Christmas, Jocelyn discovered a second one with a different period in another part of the sky. And then just after Christmas, he discovered a third one. And then it was clear this can only be stars. And these things, there was no interesting signal about it, because it was just pulsing away always with the same period. No message on it or nothing. And now the question is, what kind of star can do this? Now stars, you can have eigenfrequencies. It's like a tuning fork. If you hit a white dwarf, it starts to vibrate, and it vibrates most dense white dwarfs can vibrate with a period of about 1 second. Also, if you make it spin, it has so much gravity that you can spin a white dwarf 1 time per second before it is ripped apart by this very rapid rotation by centrifugal forces. A neutron star, when you hit it like a tuning fork, it vibrates about 1,000 times per second. It's a much stiffer stuff. And a neutron star can also spin 1,000 times per second before it is ripped apart. And so in the beginning, people thought maybe they are vibrating or rotating white dwarfs. But if you would find one which is much faster than 1 second, then you can be sure it is not a white dwarf. And within a year that happened, 2 American radio astronomers discovered that this Crab nebula, the one from 1054, that in this nebula there is a pulsar which pulses 30 times per second. It gives 30 pulses per second. 1/30th of a second is the period. They did not know where it was in the nebula because the radio telescope cannot resolve, it has a very bad resolution. But then 2 astronomers at Lick Observatory saw that this star, and it's the lower one of this binary, the double star here, this star flashes on and off 30 times per second. And here is a picture of that. This star, here is it on, then it's off, then it is on very little bit, and then it's on bright again, on faint again, on bright again, on faint again. If you make a graph of it, it gives a big pulse and a smaller pulse every 1/30th of a second. So it is 30 times per second. A white dwarf can never do that, cannot vibrate or rotate like that. A neutron star, if it would be vibrating, it would be 1,000 times per second, but spinning 30 times per second is no problem for a neutron star at all. It can easily rotate 30 times per second. And so this quenched the whole thing. Pulsars must be rotating neutron stars. And it was in the middle of a supernova remnant, just what people had predicted. So you have a pulsar here, and so this connected pulsars immediately also with supernovae, and so it confirmed what Bade and Zwicky had said. And so the idea is that the thing is emitting, like a lighthouse, beams of radio waves and also of light in the case of the Crab pulsar, but very few pulsars emit light also. But it's just like a lighthouse. Why would it have these beams? Well, one of my countrymen already in 1960 predicted that neutron stars have a very strong magnetic field. And so people already immediately thought this must have to do something with the magnetic field of the neutron star. The idea is that these beams are emitted above the magnetic poles, and you can measure how strong the field is from the breaking of the rotation. In the case of the Crab pulsar, the pulsar slows down. That was already measured by the radio astronomers who discovered it in 1968. It slows down by 30 nanoseconds per day. So it is a flywheel in the sky with a brake for some reason on it. The pulse period increases with 30 nanoseconds per day, and the brake on it is this magnetic field. If you have a rotating magnetic field, you also generate an electric field. And this variable magnetic and electric field propagate in space like a very strong electromagnetic wave, and it is an enormous magnetic brake on this neutron star. And so they spin down, and the field strength, which you can just calculate from the slowing down of the Crab pulsar, is of the order of 10 to the 12, and you call that here a trillion, I think, in America, a trillion times as strong as the Earth's magnetic field about. So that is the model for a pulsar. Now I would like to let you hear a couple of pulsars. First, one of the ones of the type which Jocelyn Bell discovered, a very slow one, 0.7 second. This is just a slow pulse. Okay. Now one which is in a supernova remnant in the southern sky, the Vela pulsar, which pulses 11 times per second. It sounds like an old-fashioned diesel engine of some sort. Then the Crab pulsar, 30 times per second. It's a bit like your kitchen blender. It's about the same speed. Now the fastest pulsars that we know are so-called millisecond pulsars. And the one but fastest of these millisecond pulsars, is spinning 642 times per second. A postdoc at our institute in Amsterdam discovered one which is spinning even more than 700 times per second, but I don't have it here, the sound, so I just let you hear what is 642 times per second, and that is this. It's not a very nice sound. It's a terrible sound actually. But this is the one but fastest pulsar that we know. Okay. Yeah, how many do we know? As I mentioned, we know already about 1,800 of these radio pulsars, and here are their positions in our galaxy. They are just sprinkled over our galaxy, and the sun is here, and the center of the galaxy is here, and of course it's a observational selection effect that we see most of them at our side of the galactic center, because that's easiest for us to observe. Now, one neutron star is already a crazy object, but two neutron stars going around each other is even more crazy, but they exist, double pulsars, and actually we know of them already 9 of these double pulsars, sorry, it should go back, we should behave. This was discovered by an Italian a graduate student, a girl in Italy, discovered these double pulsars 5 years ago. 2 neutron stars going around each other in 2.4 hours. The system fits inside the sun. It is really very small. And these 2 large masses going around each other, which thus in 2.4 hours, they disturb space. They make gravitational waves which propagate with the velocity of light into space. And that is a form of energy loss. If you have these 2 massive bodies going around each other with a high speed, even the space starts to vibrate, and that propagates away and carries away energy. Due to the carrying away of energy, the 2 neutron stars get closer together, and for these 2 you can calculate that they will collide with each other 85 million years from now. So within the next 100 million years, you don't have to worry now, but they will do that. And when this happens, you get an enormous burst of gravitational radiation, which you can see out to 50 million light years or so with antennas like we have now on Earth. LIGO in the state of Washington and in Louisiana, the best, most certain sources they can see is this colliding neutron stars. We know 9 of these double neutron stars in our own galaxy at this moment, but there must be many more, and you can calculate that also in other galaxies there are many, many of these. And so they are the most, they are the best sources at this moment of which we are sure that they can give a good burst of gravitational radiation. Now, so how does this star look at the end of its life before it just collapses, the core collapses to a neutron star? Stars first fuse hydrogen to helium, then when the interior contracts, gets hotter, it fuses helium to carbon and oxygen. Then still later it fuses carbon and oxygen, carbon to magnesium and sodium, later oxygen to silicon and sulfur, and you have still a phase of neon fusion, etc. And finally, a core of iron forms, and when this iron core, which is still normal, degenerate like a white dwarf, when it exceeds the Chandrasekhar mass, it collapses to a neutron star. And so then all the energy which is released is used to throw the whole rest of the star into space. And in this way, our galaxy is being seeded with elements heavier than hydrogen and helium. So the elements hydrogen and heavier than hydrogen and helium all comes from these massive stars at the end of life when they explode. Now, what do we know about black holes? Because if the burned out core of a star is more massive than 3.5 solar masses, they would leave a black hole. Now, also those we know, but the problem with black holes is when they are single, you cannot find them because they have no magnetic field. They probably spin, but unlike a pulsar, unlike a neutron star, they cannot do anything when they are single. They just disappear from view. And the only way we can discover black holes is if they are in binary system. And we know now about 30 of such systems in our galaxy where we have a compact object which is more massive than 4 times the Sun. And it is getting mass from a companion star. If it is in a binary, it can attract mass from the outer layers of the companion. And when this matter falls in, it is accelerated. And when it falls into the black hole, reaches the horizon of the black hole, it has about the velocity of light. But before that, it has already so much velocity that when the atoms collide with one another, the gas is very much heated and emits X-rays. So we discover them by their X-ray emission. And there's about 30 of them known in our galaxy and a couple in other galaxies. But there must be many black holes, but you can only find them if they are in this funny configuration with another star. So to summarize the final stages of stars, we now think that if a star is less massive than about 8 times the Sun, the burned out core is small enough to leave a white dwarf. The rest of the star is gently blown out when the star has become a red giant. If a star starts with a mass between 8 and about 20-25 times the Sun, the core is too massive, the burned out core, so it collapses to a neutron star. Yeah, and we do not know exactly this limit, but it's probably between 20 and 25 times the Sun. Then the burned out core, for a single star in any case, leaves a stellar black hole. And this must have happened many, many times in our galaxy, because to get the 2% heavier elements, there must have been of the order of 1 billion supernova explosions in the history of our galaxy. And of these billion, about a quarter probably produced a black hole and 3/4 produced a neutron star. So, if I may summarize, life after death for stars can still be pretty interesting. But the most important thing, you can wonder, what use do neutron stars have? Well, the use they have is that the elements which were produced in the interior of stars were kicked out thanks to the neutron star and were distributed through the hydrogen clouds in our galaxy such that a system like our solar system and our planet Earth could form from these heavier elements. And so the gold in your wedding ring, the calcium in your bones, and the silicon in your computer chip, and the phosphorus in your brains, which you need to think, of course, and then 83 of the 84 other elements than hydrogen and helium would not have existed without these neutrons, supernovae that produce neutron stars. Why do I say 83 out of 84? There is another type of supernova explosions, the type 1As, which probably produce most of the iron in the universe. So there is one element which is not produced in such large quantities by neutron stars. This is what I wanted to tell you for tonight. Thank you very much.
So as usual, we'll have questions, and wait till you get a microphone, and then at the end, afterwards, there's, as always, the refreshments in the common room. I think we could turn up the lights.
Yeah. Thank you. Thank you. As my medical colleague next to me encouraged me to say, I was fascinated and very attracted. I'm a dentist, and I was very attracted by the sound of that 600 RP per second. It made me feel very at home. If a supernova is the second life or the second incarnation of an exploded star, do we have any idea if there is another life? Do we have any idea what it may turn into or become, or what might happen to it after this sort of phase of its life?
What pulsars do is they slow down, as I mentioned. The pulse period increases. There are no pulsars known with period longer than 8 seconds. So after when they have reached a period of 8 seconds, they turn off, and we know also why this is, because the electric fields which they generate are not strong enough to pull out some charges from the crust and accelerate things. So they just die. This is a second death. And most of the neutron stars of this 1 billion or so in our galaxy are dead. They are pulsars which have stopped pulsing. The estimated number of live pulsars in our galaxy, which we could potentially observe, is only a few 100,000 at this moment. But after about 10 million years, most of them turn off. They can attract a little bit of interstellar gas, but that is hardly anything, so they just keep hanging around. And the same is with the black holes. And white dwarfs, you still see, they are radiating out the original heat they had, but they also cool and fade away after a while. White dwarfs, there are still many more than neutron stars, about 10 times more.
They just sit as a mass.
Yeah, they just keep hanging around in the galaxy, but yeah.
So this may be an unsophisticated question, but given that we don't really know what dark matter is, and that we can't measure all these billions of black holes that are not in binary systems, what is it about the two different phenomena that make them not the same?
That's a very good question. It is the total mass of these billion neutron stars and the few 100 million black holes is so small that it can never account for the dark mass. The dark mass is far more. And people have been looking for other explanations like brown dwarfs and all these type of things. But stuff made out of atoms is not dark matter. It's something else. Nobody knows what it is. But it's so much more than the atoms. It's at least six times more than normal matter, what we know. Neutron stars are normal matter. It's not dark matter. Black holes are normal. Well, black holes I wouldn't call normal matter because we don't know what happens in the center, of course. But
what's the range or diversity on the radius of the black holes? Are there limits on the low end and the high end of the radius of a black hole, and what imposes any limitations on the size of the black holes?
Oh, there is a very simple relation that a black hole of 1 solar mass has a horizon radius of 3 kilometers. And then for increasing mass, it just multiplies with this 3 kilometers. So if you have a 100 million solar mass black hole, it is 100 million times 3 kilometers for the horizon. It's very simple. It's a very simple relation. The radius goes with the mass.
But there's a definite lower end.
There is a lower end for these tiny little ones of which Stephen Hawking was thinking about, which evaporate. Yeah, but maybe David can tell me that better. What is the lower end of a black hole? It's the Planck mass, I suppose.
Well, presumably when they're small enough, your description of them would change. But
they become quantum mechanical.
And even
objects.
the big ones eventually radiate away.
Yeah, the big ones would in the end, I mean, if you have infinite time available, they would also evaporate. But even a 1 solar mass black hole, the evaporation time is so gigantic that it's not something to worry about in the near future.
So let me take the chance to ask you a question as an astrophysicist. What about other interesting compact objects such as strange matter stars or quark stars?
Yeah, well, people make models of those, of course. Yeah, that's... there are decent models of quark stars, of strange stars. And they're a bit smaller than neutron stars. Those are stars where indeed in the center you may have quarks. And it is a possible alternative for the very high densities in the centers of neutron stars. We do not really know. And we would only know if we could really measure the radii of these objects. And at the moment, that is very difficult. I mean, people have been trying to measure radii of neutron stars, and a very promising way looks type 1 X-ray bursts. Those are thermonuclear bursts in a binary system where matter is being accreted. But still the error bars are so large on these radii that we cannot distinguish whether they are strange stars or neutron stars. But the strange stars would have slightly different radii than the neutron stars. Yes.
You pointed out this one system where there were 2 neutron stars orbiting each other within the radius of the sun.
Yeah.
How did that system ever form?
That's a fantastically good question, and that's exactly my field, what I've been working on in my whole life. Making neutron stars in binary systems. And I showed you this black hole with a normal star next to it. But there are many binaries, there are about 200 binaries known in our galaxy where we have a normal star and a neutron star going around it. There is a very simple way why you could make these. The more massive a star is, the shorter it lives. So the guy who already collapsed was originally the more massive one of the two, and the other one has not yet finished its evolution, and so it can then transfer matter to the other guy. If this one also finishes its evolution, well, then there is a trick needed to keep them together, because if you explode here, if you eject more than half of the mass of the system, the two ones go in a hyperbolic orbit. But lucky enough, in close binaries, before a star collapses, it wants to become, every star becomes a giant before the core collapses. But in a binary system, there is no room for a giant. So then the outer layers are transferred to the other star. So by the time the thing collapses, it has become the less massive of the two, and you cannot emit half the mass of the system, so they stay together. And you have to do that trick another time. And then, but actually, in this case, if this one becomes a red giant, this guy will feel, it gets into the envelope of the other star, and it feels an enormous friction, and it will spiral inwards. And either it ends up in the center of that star, and then we have no clue what happens to the star, or it orbits just the compact core of this star, and at the time that this compact core explodes, then you have two neutron stars very close together.
So it's the friction.
It's the friction which have brought in the other one very deep into the other star. Yeah.
Since the neutron star is composed of neutral particles, I don't understand how you get a magnetic field generated.
Well, that's another very good question. Well, neutron stars do not consist only of neutrons, and maybe I have to see if I can get a picture of that somewhere. No, let me see. Sorry. a neutron star, the interior part is indeed, if it is, consists, it's like the Earth is built up in different layers, and it has an outer crust in which there are still atomic nuclei and electrons. And so it's not only neutrons, but there is a transition to the outside world, and those are very thin layers, but it has an outer crust where you still have normal matter, more or less, and an inner crust where you get very neutron-rich nuclei, and then finally the nuclei completely all dissolve and become neutrons if you go deeper in. But even in the center, I mean, if it's not quark stars, but even in the center, you still have some protons and electrons. And actually they are superconducting and superfluid, and all kinds of interesting physics is happening there, and you can have a very strong magnetic field anchored in the crust, in the normal matter of the crust. And the idea is, every star has a magnetic field. And if you just let the star collapse, the surface shrinks so much that if you conserve what we call magnetic flux, then you get an enormous magnetic field. And this is why in 1960 already Lodewijk Woltjer, a former Dutch one, but working at Columbia University, predicted that neutron stars have fields like this 10 to the 12 Gauss. Yeah. But he did not predict rotation. He thought he was working on the Crab Nebula, and he thought there was a neutron star there, but not rotating. And he thought that neutron star was accelerating by its magnetic field particles, but it does not work.
Question I think I can talk about now. I saw a theory about other universes coming out of the center of a black hole. Have you seen that theory?
Well, yes, that is Lee Smolin from the Perimeter Institute in Canada, who has this idea that black holes make new universes, and there's even a kind of Darwinistic evolution of universes through this by means of black holes. I am not the person to judge how believable that theory is, but Lee Smolin is a very smart guy, so that's the only thing I can say. I don't know what David thinks.
I think you're very kind.
Okay.
Any other questions? Well, let's thank Ed again and refreshments. Thank you.